Okay, let's take a look at how to sketch the graph of f at x equals x cubed plus 3x squared minus 4x over x squared plus x minus 6. And we'll be taking a pre-calculus approach here. That is, we won't concern ourselves with too many specific details. We'll just look for the overall shape of the graph of this function. In order to see several of the characteristics, it would be really nice to have this function in factored form. So let's look at factoring both the numerator and the denominator. Now notice that our numerator here has a common factor of x. So if we common factor out x in the numerator, we get x times x squared plus 3x minus 4. Our denominator is a trinomial that can be factored. We're looking for two numbers that multiply to -6 and add to 1. Those numbers are 3 and -2, so we can write the denominator as x plus 3 times x minus 2. We can further factor the numerator here. It's a trinomial, looking for numbers that multiply to -4 and add to 3, and those numbers are 4 and -1. So we can rewrite that numerator as x times x plus 4 times x minus 1, and our denominator is still x plus 3 times x minus 2. And that gives us the factored form for our function. So let's start talking about some of its characteristics, beginning with its domain. Well, notice we can use any x value we want here except for -3 and 2, because those values make the denominator work out to 0, and we know we cannot divide by 0. So our domain is x as an element of the real numbers such that x does not equal -3 or 2. And we'll move on to intercepts for our function here, starting with the x-intercepts. Well, the x-intercepts are the x values that make our function work out to 0. And notice that if the numerator works out to 0, our entire function is going to work out to a value of 0, provided that the values that make the numerator work out to 0 don't also make the denominator work out to 0. That's not going to happen here, though, because we do not have any common factors between the numerator and the denominator. So what are our x-intercepts? Well, looking at the numerator, what makes it work out to 0? Well, the value of 0 for x, -4, or 1. So those are our x-intercepts, 0, -4, and 1. For the y-intercept, we want to find the value that we get when we make x 0. That is, we want to find f at 0. Substituting 0 into our function gives us 0 in the numerator and -6 in the denominator. 0 divided by -6 is just 0, and that's our y-intercept, which of course we should have seen coming. I mean, we do have an x-intercept of 0, which is going to be right on the origin. Therefore, we actually know right away we have a y-intercept of 0. So we have our intercepts. Let's move on to asymptotes and holes, starting with vertical asymptotes. Well, for this, again, we want to look at the denominator. What values make this denominator work out to 0? -3 and 2. And those are our vertical asymptotes. Just make sure that those values don't also make the numerator work out to 0, because if they do, that means we'd have a common factor between the numerator and the denominator, and in that case, we end up getting a hole. But that does not happen here. We have no common factors between the numerator and the denominator. So our problem values of -3 and 2 are going to result in vertical asymptotes. So the equations of our vertical asymptotes are x equals -3 and x equals 2. Now what about a horizontal asymptote? Well, we need to look at the degree of the numerator and compare it to the degree of the polynomial in the denominator here. And in this case, we have a higher degree polynomial. We have a degree 3 polynomial in the numerator, and we only have a degree 2 polynomial in the denominator. So we have a higher degree in the numerator than in the denominator. So we will not have any horizontal asymptote in this case. We only get a horizontal asymptote if the degree of the numerator is less than or equal to the degree of the denominator. So none for horizontal asymptotes. But we do have a linear oblique asymptote. And we know that because the degree of the numerator is exactly 1 higher than the degree of the denominator. And we need to calculate the equation of that oblique asymptote, that line. And how do we do that? Well, we actually divide. We're going to divide this polynomial in the numerator divided by the quadratic function in the denominator here. And how do we divide? Well, we're dividing by a quadratic here, so we're going to use long division. Now, before we do that long division, you might be asking, why are we going to divide? Well, the reason is because we want to write this function in a different form that allows us to clearly see the equation of the linear oblique asymptote. So let's take a look what happens here. We have x cubed plus 3x squared minus 4x. I'm going to write in a plus 0 here because there's no constant term written up here. And we're going to divide it by x squared plus x minus 6 using long division. So we'll give you a little review of polynomial long division here. We start by doing x cubed divided by x squared. That gives us x. So we'll write it there, and we'll multiply that result by the entire divisor, which gives us x cubed plus x squared minus 6x. And we'll do some subtraction. X cubed minus x cubed is 0. 3x squared minus x squared is 2x squared. Negative 4x minus negative 6x is 2x. And we'll bring down that 0 term and write it at the end here. And we'll repeat the process. Let's divide again. We'll do 2x squared divided by 1x squared, which just gives us 2. So we'll write plus 2 up here in our quotient. And we'll multiply that result by the entire divisor. That gives us 2x squared plus 2x minus 12. And once again, we'll subtract 2x squared minus 2x squared is 0. 2x minus 2x is 0. 0 minus negative 12 is 12. So we can rewrite our function here as x plus 2 plus our remainder of 12, which has not yet been divided by this quadratic expression. In other words, we get this, x plus 2 plus 12 over x squared plus x minus 6. Now, why would we want to write this like this? Well, if we're looking at our oblique asymptote, we're really interested in what happens as x approaches infinity or negative infinity. And if we think of what happens to this expression, in particular this last part of the expression, when we start subbing in really big x values or really negative x values, what happens to this part of the expression? Well, it approaches 0. We have 12 on top divided by some number that's either becoming a very large positive or a very large negative in some cases on the bottom here. But the point is, the bottom is growing much more rapidly than the top. In fact, the top's not growing at all. So the value of this entire fraction starts to approach 0 as x approaches infinity or as x approaches negative infinity, which means it kind of starts to look negligible, starts to look like nothing. So as x goes to infinity or negative infinity, our function starts to look more and more like y equals x plus 2, which is a line. And that is the equation of the line that is our oblique asymptote, y equals x plus 2. Now keep in mind, if we were dividing by something linear here, you wouldn't have to use long division. You could use synthetic division. But in this case, we were kind of stuck with long division. Okay, in terms of wholes, wholes happen when we have a common factor in the numerator and the denominator, and we do not have that here, so we have no wholes. All right, so there are our asymptotes and wholes. Let's move on to the final piece of the puzzle, which is our positive negative intervals. So we'll do this again using a chart. We're going to look at several intervals and check out the sign of our function on those intervals. How do we get the intervals? We use values at which the function could change from positive to negative or vice versa. And those values are our x-intercepts and our domain issues, which in this case are our vertical asymptotes. So we'll start with the lowest number there, which is negative 4. We'll look at everything that's below negative 4 for x. Then we'll look at x values between negative 4 and the next highest value here, which is negative 3. We'll go then from negative 3 to the next highest value of 0. Then we'll go from 0 to 1, which is the next highest. And then from 1 to 2. And last but not least, all x values above 2. So let's look at each of these intervals and figure out the sign of our function. We'll do that by subbing values into our factored form and looking at the sign of each factor on its own. Starting with x values that are less than negative 4. So let's use an x value of, say, negative 100. If we sub that in, what's the sign of each factor here? Well, if x is negative 100, x is going to be negative. Negative 100 plus 4 would be negative. Negative 100 minus 1 is going to be negative. Negative 100 plus 3 is going to be negative. And negative 100 minus 2 is going to be negative. So in the numerator, we have a negative times a negative times a negative, which is a negative. In our denominator, we have a negative times a negative, which is a positive. And a negative divided by a positive gives us a negative result for all x values less than negative 4. And we can do the same thing for our other intervals. And I'll move fairly quickly here because we're really just doing the same thing over and over again. If we subbed in a value between -4 and -3, the signs of our factors would be negative, positive, negative over negative times a negative, and that result ends up being positive. If we choose a value between -3 and 0, perhaps -2, our signs are negative, positive, negative, positive, and negative, and that result ends up being negative. From 0 to 1, sub in, for example, 0.5, our signs end up being positive, positive, negative, positive, negative, which gives us a positive result. From 1 to 2, perhaps we could use a value of 1.5. Our signs are positive, 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 negative, and that result is negative. And last but not least, if we use x values over 2, for example, 1,000, you'll get a positive, positive, positive over a positive times a positive, which of course is a positive result. So there are the intervals on which our function is positive and negative. And we now have enough to sketch a decent sketch of this graph. So let's just summarize all of that information one more time. For our function f at x, we have our domain, x cannot be -3 or 2. We have our intercepts, 3 x-intercepts and our y-intercept. We have some asymptotes. We have vertical asymptotes at -3 and 2. And we have a linear oblique asymptote of y equals x plus 2. Last but not least, we have our intervals over which our function is positive and negative. So here we go. Let's finish up with our actual sketch. Let's get some of this information here on our graph. And we'll start with our x-intercepts of -4, 0, and 1. So -4, 0, and 1, those are our x-intercepts. Our y-intercept of 0 is already plotted because it's also an x-intercept. And we have some asymptotes, vertical asymptote at -3 and a vertical asymptote at 2. For our oblique asymptote here, we actually need to sketch the line y equals x plus 2. So this has a y-intercept of 2 and a slope of 1. So we can plot that y-intercept of 2, and our slope of 1 just means we're going to go over 1, up 1, over 1, up 1, and so on, until we can see the line, at which point we can just draw it. Now keep in mind these points that we were plotting here in green are not actually points on our function. They're just points that helped us get that oblique asymptote. So I'm going to get rid of those points now. And now we are ready to draw the graph. So it all comes down to the positive, negative intervals at this point. And when we're using x values below -4, our graph, our function, should be negative. Okay, now how are we going to do that? Well, we need values to be negative when our x values are less than -4. So we're going to be looking at down here. Now we have to follow this asymptote. So our graph's probably going to be kind of following along that asymptote and staying negative right up until we hit that x-intercept. And at that point, from -4 to -3, our graph becomes positive. Well, that makes sense because we have this intercept that we have to hit, and then we have to follow that vertical asymptote. So we could probably do something like this. In fact, that works out quite well. We'll draw the piece that's negative along the asymptote until we hit that x-intercept, then go positive and follow this asymptote. All right, so that looks like that. Now, what happens past -3? Well, from -3 to 0, our graph is going to be negative, so we're going to be down here somewhere. Of course, we have to follow this asymptote, so we're probably going to do something like this until we get to that x value of 0, because we're supposed to stay negative until we get to 0. But from 0 to 1, we go positive. So here's an x value of 0. Here's an x value of 1. And we need to be positive between those x values. So we must have to go up somehow and then turn around to get back to this. Keep in mind our linear oblique asymptote doesn't really apply in this area. It only deals with the end behavior of our graph as x starts to approach infinity or negative infinity. We can kind of ignore the fact that we have a linear oblique asymptote in this area here. It's only for the end behavior. So we're going to go positive from 0 to 1 because that's what we're supposed to do. But then from 1 to 2, our graph is going to be negative. Well, from 1 to 2, we got to stay negative and we have to follow this vertical asymptote. So we must be doing something like this. So negative from -3 until our intercept at 0, positive until 1, and then negative again until 2, gives us a curve that looks something like that. Okay, and then last but not least, we need to deal with x values greater than 2, in which case our function should be positive. So we're going to be positive up here, but we have to follow our asymptotes, our vertical asymptote, and as we approach the ends of our graph here, this linear oblique asymptote. So how do we do it? Well, we have to stay positive, right? So we're not going to be coming in from the negatives or anything like that. We must be coming in from the positive values along that asymptote, and then eventually start to approach that linear oblique asymptote, staying positive the whole time. So that's what we get. And if I remove the asymptotes here, you get an idea of what this function looks like, and it's pretty complicated looking, isn't it? But that's it. That's a sketch of the graph of f at x equals x cubed plus 3x squared minus 4x over x squared plus x minus 6.